Hello and welcome. We're going to get into creating our triangle now. Before we get into that, I'm just going to ramble a little bit about some of the big concepts of OpenGL. So back in the day, a lot of the speed of computer graphics was in algorithms and things, and currently the major bottleneck is the bus between the computer and the graphics card, the data bus. So a lot of the current improvements in graphics are around things like memory management and scheduling and data transfers and all of that. And one of the upshots is that a lot of new language has spread up. One concept that I'm going to use a little bit is client versus server language. Now, I'm not talking about the internet. This is graphics programming. Think about it like this. The client is our computer with our CPU and our RAM and everything. And the server is the graphics card with its GPU and its VRAM, its video RAM, and all of that. So the goal, basically, is we will create our data on the client side and then upload it to the server side, if that makes sense. Okay, but I just wanted to talk about that language a little bit because it does come up, especially in newer generation APIs. Okay, so to start with, we want to declare the data for our triangle, and the format of the data will be X, Y, Z, then followed by red, green, blue. Okay. I'm going to use a vector for this. A vector is like an array, except we can resize it on the fly. Okay. There's no particular reason to use a vector. We could use an array just as well, but why not? So we'll include vector, and then down here, okay, so now I'll put in this data. So we're going to use something called normalized device coordinates. So for the X, 0 is at the center, -1 is to the left, +1 is to the right. So this is pretty close to the center. And then, let's see if I can remember this correctly. I believe it's the opposite in Vulkan, which is like the next level graphics API. In OpenGL, I believe +1 is upwards and then -1 is downwards. Okay, so we have -0.25. And a Z value of 0 is at the Z level of the screen. So not far away, not close, but at the screen. Okay, so we'll just do the standard. So one vertex will be completely red, the other one will be completely green, the other one will be completely blue. Okay, so this is how we would do it if we were defining a single vertex. 2, 3. This one will be completely green. This one will be completely blue. Okay, and then we want to stay down and just go to the right a little bit, and then we'll be dead center on the X, and we'll just be upwards. Okay, that is looking good. Okay, so that is on the client side. Now we will create, also we'll have, this might be useful, we'll just keep track of how many vertices we have. Now we'll create what's called a vertex buffer object, which will store all of that as a single list on the GPU, on the VRAM. So we'll go VBO for vertex buffer object. A buffer is just a big list of data, a set of data. Now, you might be saying, wait a second. If you're familiar with OpenGL, and I'm going to get a little bit esoteric at this point, if you're familiar with OpenGL, you may remember that it's more common to say GL gen buffers with exactly the same signature call. The difference between gen buffers and create buffers is that create buffers was the way to do it since about OpenGL 4.5 or 4.4. The problem with gen buffers is in the underlying implementation. Okay, so let's say we have 12 objects, so we generate 12 buffers, and then we want to do something with buffer number 7. We would have to make a call to bind buffer number 7 as the current buffer and then work with that. But it gets a bit annoying doing all those calls. So instead, what we want to do is something called DSA, or direct state access, where we just tell OpenGL, okay, I want to do this on buffer number 7, and it works directly. We don't need an indirect call. And then the thing is, OpenGL is commonly implemented in C, which does not have function overloading. So in order to get around it, the creators of OpenGL simply created these other functions, which instead of gen, they say create. So I'm giving you the short story, but that's basically it. So let's pass that data in. So the modern way to do it is we call GL named buffer storage, and it takes in the buffer, which is our VBO, size. Now, I believe, what is the size? Well, if we go vertices.size, that is the number of items in our list. We've got, what, 18 numbers there? But then we need the size in bytes. So we could say that times 4, because typically a float is a 32-bit number. But just to be completely dynamic, we'll go size of float. Okay. Next is constant void pointer data. So remember what I said about strings. If you have a list is really a pointer to the first element. So what we'll do here is we'll go vertices.data. That works with the C++ Vertex vector class. It returns a pointer to the beginning of the data. That's what we need. And then flags. So the flags I'm going to use here are GL dynamic okay, so dynamic storage bit basically means that we send this data in, we allocate this amount of storage, but it's in a place where we can change it on the fly. It's the most general sort of thing. Now I'll copy this in. I got this from just looking up on Kronos Group's Wikipedia, but the different things we can pass in. So dynamic storage may be updated after creation through GL buffer subdata. I don't know, we might look at that, might not, might be a little bit advanced for this course, I don't know. Map read, so what this means is, okay, so we allocate the storage on the server side, on the GPU, and then in order to do anything with it from the program side, we map to that memory. So this is saying after we map to the memory, we're allowed to read to it. And down here, after we map to the memory, we're allowed to write to it. We can put in combinations of these options together. You can see I'm kind of glossing over this. Dynamic storage is the way to do it. Yeah, okay. Map persistent, so we can be working with the data at the same time that the GPU is working with it. Coherent, when we do any update operation, that is performed immediately. It doesn't spawn off to a different thread, which might be delayed, might take a bit of time to do an update. Or client storage, where instead of storing it on the GPU, we store it somewhere in our RAM. Okay, so those are some different options we can pass in. Right, but remember, all we've done right now is we've trucked a shipload of data to the graphics card. But the graphics card has no way of knowing. It would be reasonable to guess at the first three are the X, Y, Z, because that's attribute number 0, but there's no guarantee of that. We could have done something where we go like X, Y, Z, something like that. So we need to be explicit about our attributes. So we have something called a vertex array object. And what a vertex array object does is it stores the set of data plus the instructions about what the data means. So we'll go unsigned int vertex array object. And this is commonly, it's a little bit overwhelming at first. I found it overwhelming when I first learned it, but it does get easier. So then we call GL create vertex arrays. We're going to create one, and we're going to store that in our VAO. Okay. Then we need to bind the vertex buffer in with the array object. So we call, not vertex. Okay, GL vertex array, vertex buffer. Okay, and it says here we need the VAO object, which is our vertex array object, and then the binding index, so we can actually bind multiple buffers to a vertex array object. In this case, we're just going to bind one, which will be index 0. The buffer that we're binding is our VBO, not our VBA. The offset. Okay, so we are starting from the start, so we'll have an offset of 0, and then the stride. So I'll just show you what we got here. The stride is from one number, this is the x. How many numbers do we have to skip to get to the next x coordinate? So here we go, 1, 2, 3, 4, 5, 6, and then we're at the next x coordinate. So our stride will be 6 floats. So we just do that size of float. 24 bytes, right? Because each float is 4 bytes, but there we have it. Okay. So that essentially binds this in so that when we allocate the storage for the VBO, that is understood by the VAO as well, which is why we need to declare the VAO before we do any VBO work. Yeah, it's a little bit much, but let's keep going with this. So the next thing that we need to do is we need to create attribute pointers to tell OpenGL what this stuff means, how to access it. So okay, so it says, what are we doing? VAO object and the index. So we are, on our VAO, we are enabling attribute 0, which is the position. Okay, so then we'll go create this. Vertex array attribute format. We need to pass in our VAO. attribute index is 0, that's position is index 0, the size. Now, position is 3 numbers, so we'll put 3 elements. The type is float. Normalized is indicating, should we normalize coordinates? This is false because our coordinates are already in the range of -1 to 1, so no normalization is needed. Relative offset, so that's 0 for the position. The position starts at the beginning of the vertex. The vertices array starts there. Okay, cool. Then what we need to do is we'll go pretty much just activate that. So that is on our VAO, attribute 0 is with binding 0. Okay, cool. So we've got that. Now let's have a look at the next attribute, which is color. Okay, so color is index 0. Sorry, 1. Yep, it's red, green, blue, so 3 components. They're floats, do not normalize them, and their offset is 3 floats worth of data. Okay, that is looking good. Just double checking. Yeah, great. Okay, so now how to actually draw this stuff. So now we've been having fun so far. Okay, and by the way, I could take all of this stuff and put it out into its own function. However, there are a few things needed, so I'll probably save that for later when we break this out into external, like separate classes. That'll work a bit better. Okay, so what do we do? Let's start drawing things. First thing we'll do, we could have done this a lot earlier, is we'll declare our color for clearing the screen, and that just takes red, green, and blue, and alpha. Let's go 0.5, 0. By the way, if I just write these 0 point things, then C++ interprets them as doubles, which are 64-bit floating numbers. I want them to be float, so I put F. That's the reason I put that F. Okay, then I go ahead and clear the screen. So I clear the color buffer, and then I make sure I'm using my program, which is not a big deal right now because we only have one program and we already used it. But when we get into a more complicated system, it's a good idea to get into this practice. So just note here, when we go to draw this, we're drawing array data because it's from an array object. We have some different options. We can, if we want, draw points or lines or anything. The shape assembly topology, which we're going to use here, is triangles. Okay, so we pass in the, so we start from index number 0, and how many do we draw? Well, that depends on our vertex count. Okay, so that's it. That is looking good. The last thing we'll need to do is we'll need to free up the memory. So we delete. So we delete our vertex buffer object and our vertex array as well. Okay, that looks good. Now, fingers crossed, let's see how this works. Nice. Cool. I hope this is working. As a matter of fact, it is. Awesome. So that's it. It seems like a lot of work, but we've got our first triangle on the screen. That is actually the hardest thing. The rest of the stuff we're doing will just be building on this. In the next section, I guess, let's have a look at textures. Anyway, see you then, and yeah, have fun. Bye.